So now we know that if you have a superposition of two states, there will be time evolution in the sense that you can observe something actually changing, okay? And so that's going to be an important ingredient in understanding how light interacts with molecules. If light causes superpositions, then those superpositions can cause changes in, for example, the dipole moment. And that dipole moment changing is going to be related to transfer of energy from the field to the molecule. Okay, so what we're going to do now is we're going to look at one more aspect of what may or may not be changing when we have such a superposition state. In your problem set or in one of the solutions, I think one of the simulations that we have, you can play around with these superpositions of some standard problem like a particle in a box, and you can see what happens to the wave packet shape as a function of time. And you could, in principle, also calculate the position or the momentum or any other variable, any other observable that you can imagine constructing. So what we're going to do now is we're going to look at the probability. All right, so we have a wave function, or we have a state vector, whatever you want to call it, that we set up. It evolves in time. It's a superposition. And now what we want to do is we want to ask the question, at time t, what is the probability that the system is in one of the eigenstates, one of the Hamiltonian eigenstates? Let's call it M. So for example, if we had a superposition of the ground in the first excited state, this might be asking, what's the probability that we're in the ground state as a function of time? Okay? Because you might think that there's a tendency to think of this as we're oscillating between two states. Let's see if that's true or not. Okay, so to calculate the probability of being in some state, what we're really asking is what's the projection or the scalar product of our state vector along the direction of the state that we're asking about as a function of time. All right. That's now, since a scalar product can be complex, to turn it into a probability, the probability is going to be that we're in the state M at time t is equal to this. This is the scalar product inside, and then we take the square modulus of that to figure out what the probability is. So that's how we define the probability. Okay, so this is straightforward. We know how to calculate all this stuff, so let's just work it out. we know what the wave function will be at time t. Right? It's going to be u, the time evolution operator on the initial state, operating forwards. Okay, so let's work out the scalar product, and then we can always square it at the end. So the scalar product is this by m. Then we have u, t naught, operating on the initial state vector, which we're going to just call the one that we've been using, phi m plus cn phi n. Okay, and so we know how this works. The time evolution operator, right, has the Hamiltonian in it, but it's operating on one of or the other basis vectors of that Hamiltonian. So that'll replace the Hamiltonian in the operator by the eigenvalue associated with each of these different eigenvectors. That'll convert it to a phase, and then we'll look at what happens on the left-hand side. Now, it's a good idea to think ahead, to try to see what is going to be the result before you go through and do all of the steps. Since this is just going to be a phase, it's going to be a number, that means we can slide all our Tetris pieces across, right? And they distribute. So you're going to get phi m times phi m times phi n. Okay, and what do we know about phi m phi n? That's going to be the Kronecker delta. And if they're not the same, then that means it's going to be 0. Okay, we'll go through it. So what you're going to see is the only term that will survive is this term, unless, of course, there's only one state, right, that they're both m, and then we don't have a superposition anyway. Okay, so let's see what happens. Now we switch this to the Em times T minus T naught times Cm by M plus E to the minus I over H bar En T minus T naught Cn phi n. Okay, so we just wrote what U is, knowing that the H is going to turn to the E's. All right, then we bring in the vector part, and we have this exponential part. Cm, and then phi m, which is equal to 1, plus exactly the same thing, but for the n case. Now I can write all this out, but what we know is going to happen is we're going to have phi m times phi n, right? So that's delta mn. So for the case where m is equal to n, then we don't have a superposition, right? And then we know, of course, the system will have just been in state m to begin with. So what we're going to do is not even think about this as the delta, because we know that m is not equal to n. So we'll just set this is equal to 0 then. This term here is 0. Okay, and so what we end up with after all of that, when we square the number. Now what happens to the exponential part? Well, it goes away, right? Because of e to the minus I something or other, then we're going to take the mod squared, so we're going to multiply it by itself with the complex conjugate. So the e to the I over and stuff is going to be multiplied by e to the plus I. Everything's the same. So that becomes 1, right? So at the end of it all, we have Cm squared. That's 1. All right, so whatever the phase of Cm it was, or whatever the complex part of it, doesn't matter either, okay? So what you see then is what this is telling us is in the superposition, the probability that you're in any one of the states that we were made, from the superposition, is just the value, the magnitude of that contribution at time 0. It never changes. Right? So that means although other observables of the system will change, the amount of the contribution, or if you want to think of it like the recipe, will have the same ingredients throughout. The only difference is their relative phases. Okay, and of course you could apply this to just as equally to the state n, or even more generally, you could have had a wave function like this, which we can say sum over k, c sub k, phi k. Now we don't just have two states. We have every possible, eigenvector of the Hamiltonian. We would do the same thing, so we can find the probability of being in the state j by evolving the state forward in time. Right? So what's going to happen? We're going to have the sum on k, phi j, u, I'll leave out the time things for now, just t and t naught, right? Ck, phi k. And what you can immediately see is all the u is going to do is turn into a phase. So it'll come out, the c is a number, it'll come out, and you're just left with phi j, phi k, times whatever that phase is. The phase is going to go away when you take the square of this. And that's just equal to then whatever is left over. It's going to be delta jk times ck squared. Right? And then summing. So if we assume for logical sense that that these all correspond to different eigenstates or eigenvectors, that makes the most sense, then only one of them will be right. Sorry, only one of them will be non-zero, right? The one when j is equal to k. So this is just the j, you can call it cj. Because what delta jk does when you do it over sum is it means you have the sum of all these terms, and only one of them is non-zero. We're going to use this a lot, to use deltas to kill off sums, right? And so this just tells you that you can go through now and check every single ingredient or every single contributing eigenvector, and this parameter will tell us how much of that is. Now this is going to have a name. I'll just tell it to you now. All right, this is going to be called the population. You would say the population of the jth eigen, whatever you want to call it, eigenstate, vector, etc. All the terms that we kind of use interchangeably. All right, so population and, like, let's say probability are the same in this context. In the next thing that we do, which will be to introduce the density operator, we will distinguish between things that we call populations and things that we call coherences. Now, one thing I want to point out, remember when we did the Heisenberg versus Schrodinger pictures, all we did was change how we put our parentheses when we looked at expectation values of an operator as a function of time. Here we can do something very similar. So let's go back to PM. The time part of this is not the most important thing. Right? The time can be there as well, but it can also be true if you don't consider the time. Let's just see what this looks like. Phi m is the state, right? And that's the definition. If we expand this out, right, which just means multiply this thing by its complex conjugate, and we have our recipe for that. That's phi m psi phi m. Notice what this is. This is the probability of being in a state M is actually the expectation value, or not the expectation value, but the matrix element, the MM matrix element of this thing here. This is an operator. We'll define it later. If you've heard of it, it's called the density operator. So this is the MM element of the density operator. That's one way you can write this. But I can move these around. These are numbers. Because this is also equal to, just writing it the other way around, phi m psi. All I did was change the order. It's just analogous to moving the parentheses around for a Schrodinger picture, Heisenberg picture. And what do we see now? It's a little bit different. This is some operator, which we've defined earlier. This is called the projection operator. Right? And it's a projection onto the state M. It's phi m, whatever. And psi is the state of our system. So this is actually the expectation value of a projection operator. Okay, so you can either think of the probability of being in a certain state as a particular diagonal element of the density matrix, or density operator. We'll go through density operator more in the next lecture segment. Or you can view it as an expectation value of a projection operator. Sometimes one viewpoint is more useful than the other. At the end of the day, of course, we usually just want to calculate something, so you don't even need an interpretation. But I think it's helpful to be able to see how these different words, they sound different, but they actually mean and they relate to the exact same quantities.